The ancient Greek philosopher Plato once said, "The measure of a man is what he does with power." For modern portable embedded systems, one could paraphrase, "The measure of a product is how little power it uses." And in this webinar, we will look at how a measure of this important hardware attribute can be obtained using the MPLAB Real-ICE and Power Monitor plug-in board. It is actually energy consumption that is critical for embedded projects that require low running costs or that are powered by battery. But the energy figure is determined from the power being consumed and how long this consumption takes place. If the supply voltage remains constant, then power is proportional to the current drawn by the hardware. Being able to measure current, therefore, is extremely important and enables a product's battery life or running costs to be estimated. The Microchip MPLAB Real-ICE Power Monitor can be used with the MPLAB Real-ICE Debugger, MPLAB X IDE and MPLAB XC compilers to measure and display current and voltage versus time. This can be measured for the target board or just the device, and can be performed when the hardware is running real-world code. You can also use it to profile the current drawn for each function and to ensure that an arbitrary peak current is not exceeded. There are several connections required before you can use the power monitor with the MPLAB Real-ICE debugger. The power monitor board plugs into the debugger and replaces the standard driver board, which you must first remove. The power monitor uses both Real-ICE connectors, so you must remove any connected logic probes as well. There are several ways to connect the power monitor to the target board. Shown here, the modular cable is being connected. This is the simplest connection method and allows measurements of only the target board current. Connect the power supply to the power monitor board and ensure the Real-ICE USB cable is connected to the debugger and your host PC. Using the modular cable from the power monitor to the target board is the simplest connection. The other two connection methods, tabulated here, require additional wiring to either the channel A or channel B terminal blocks on the power monitor board. These connection methods allow target board voltage to be monitored, as well as current, and can also be used to monitor the voltage and current of the actual target device, rather than the entire board. Before initial use of the power monitor, you must download the MPLAB X IDE Power Monitor plugin. Do this inside the IDE by selecting Plugins from the Tools menu. In the dialog, select the Available Plugins tab and click the checkbox next to the Power Monitor item. Click Install and follow the prompts. There are several selections associated with the Real-ICE and IDE that need to be made before using the power monitor. When you create your MPLAB X IDE project, it must be configured to use the Real-ICE debugger. When asked for a plug-in board, select Power Monitor. Both these options can be set for existing projects from the project's Properties dialog, as shown here. Other options need to be set in the Real-ICE category. Under the Power option, select Power Target Circuit from Real-ICE and confirm the operating voltage of your target. For the first demonstration, we are going to capture current versus time, so go to the Trace and Profiling option category, and for data collection, select Power Module. You should see the Ready LED on the power monitor turn green when connection is established with the debugger. Let's now see the power monitor in action. Our project is already set up for Real-ICE and the power monitor as just shown. In this example, we want to capture current versus time. Reopen the Project Properties dialog and the Real-ICE category. Go to the Trace and Profiling option category and check that the Target Power Sampling selection is set to Power Data Only. This indicates that current will be measured along with the timestamp. Confirm also the sampling interval, which is the rate at which samples will be taken. Open the Power Monitors window from the Tools menu, Embedded Power Monitor. Let's build and debug some code using the Realize debugger. The code will illuminate one of the LEDs connected to a port. After each timer interrupt, the adjacent LED will also be illuminated. Once all 8 LEDs are turned on, the following interrupt will turn them all off, and the cycle repeats. A breakpoint has been set in this code to stop after 5 iterations of this cycle. Now that the code has stopped, let's look at the Power Monitor window to see what we captured. In this graph, current is drawn vertically against time. You can clearly see the current ramp up as more LEDs are turned on. Then it drops markedly when they are all extinguished. The graph is indicating that each LED is drawing just over 1 mA. You can also see the period of the loop, just under 250 milliseconds. There are various graphing controls shown on the left of the window. You can enlarge the data display to take accurate measurements using the zoom button or a mouse gesture. All the breakpoints have now been removed from the code. Instead, let's have the code break if the current exceeds a threshold value. Again, open the Trace and Profiling dialog. Note that you can get to this dialog quickly using the uppermost shortcut button on the left of this window. Enable the Break at or above specified current level checkbox and enter the current threshold in the field below, in this case 20 mA. Let's run the code again. Execution has halted, and in the Power Monitor window you can see that this has occurred when the current exceeded 20 mA. Execution has stopped at the line of code which wrote a value to the LEDs. As with any breakpoint, you can now check the contents of variables, such as port count, which determines the value written to the LEDs in this example. Engineers face difficult challenges relating to power. Code that executes fast can quickly return the microcontroller to a low current sleep state, but the current drawn by a microcontroller will, to some extent, be dependent on the instructions being executed. Hardware designs that minimize components also reduce the current consumption, but this choice may require additional code to compensate for the loss in functionality. How do you get the optimal energy consumption for a set of design guidelines? By using the MPLAB X IDE's code profiling feature in conjunction with the Power Monitor, you can assess how firmware is affecting the power consumption of a target system. To use the code profiling feature, reopen the Realize category in the Project Properties dialog. Select Trace and Profiling and change the Target Power Sampling selection to Power Data on PC Update Only. When this is selected, the Power Monitor display will be updated only when certain points in your executing program are reached, specifically when the code enters and exits each function. Your MPLAB XC compiler will automatically insert into the binary image additional code which communicates with the Power Monitor so it can record when functions begin and end. You will see the code size of your project increase, and if you happen to look at the compiler-generated code, you might see additional calls to entry and exit routines. With code profiling enabled, I'll now rebuild and run the same project. After I pause execution, you can see the function profiling information tabulated beneath the current and voltage graph in the Power Monitor window. The name of the function being entered is shown, along with the program counter value where the function's entry routine is called. The name return is shown where the previously listed function exits. My test program is only trivial, but you can see the function main being executed, the interrupt routine being triggered repeatedly, and where each interrupt routine returns. You can see the current at each of these points in the table, and how long each function takes to execute. Click any line of the table to highlight the corresponding point in the graph. Prudent use of functions in your code can reveal how your code is affecting the energy requirements of your target system. In this webinar, we have seen that the MPLAB Real-ICE Power Monitor board is a valuable tool for projects that have power constraints. It can display current voltage plots, revealing your hardware's rate of energy consumption. Current threshold breakpoints and code profiling allow you to determine which parts of your program draw excessive current. The Power Monitor is compatible with the current versions of MPLAB X IDE and all MPLAB XC C compilers, and can be used with all PIC devices.